3I Atlas is producing two distinct tails that violate fundamental comet physics, with the toward-sun tail requiring a mass density 1 million times greater than the solar wind to maintain its 600,000-mile length. Recent observations from November 22nd and 24 captured these structures extending millions of miles into space, staying remarkably narrow and focused like laser beams instead of spreading out like normal comet tails. The object sits 186 million miles from Earth right now, exactly twice the distance between Earth and the Sun. At this distance, something extraordinary is happening that contradicts every model of how comets should behave. The recent image from November 22nd was captured by an amateur astronomer using a half-meter telescope. This instrument collects significantly more light than smaller telescopes, allowing it to see fainter and more distant objects. The image shows a bright glowing coma around the nucleus with two distinct structures extending outward. These are the comet's tails, but they break the rules. The tail stretching away from the Sun extends about 3 million miles. The other tail, pointing toward the Sun, measures about 600,000 miles long. Both tails maintain an unusually narrow, focused appearance across their entire length. The November 24th observation confirmed these same features. Even though 3I Atlas was only 15 degrees above the horizon, making observation extremely difficult, the identical structures appeared. Multiple independent observers are recording the same unusual features, which confirms these are real physical structures, not imaging artifacts. Normal comet tails spread out and become fuzzy as they extend into space. The particles disperse, creating a fan-shaped structure that widens with distance. But 3I Atlas maintains tightly columnated jets across millions of miles. This focused beam structure has never been observed maintaining itself for this duration in any comet. The 5-to-1 ratio between the tail lengths reveals something significant. The away-from-sun tail has help from solar radiation pressure and the solar wind, both pushing particles in that direction. But the toward-sun tail fights directly against these same forces. Every particle in that anti-tail pushes into the solar wind, like swimming against ocean waves. Harvard astrophysicist Avi Loeb calculated the physics required for this anti-tail. To create a 600,000-mile-long structure fighting against the solar wind, the material density needs to be about 1 million times greater than the density of the solar wind itself. This is not typical comet outgassing density. This represents something else entirely. The 5-to-1 ratio between these tails is not changing. Earlier images showed the same proportions, and the November observations confirm this stability. Whatever mechanism creates these jets maintains consistent physics across hundreds of millions of miles through space. Comets usually show wildly fluctuating activity. As they rotate, different ice deposits get exposed to sunlight, creating variable outgassing patterns. The jets sputter, shift direction, and change intensity. But 3I Atlas maintains this stable asymmetric jet structure, observation after observation. The mass loss problem presents another violation of standard physics. These tails consist of material evaporating from the comet due to solar heating, a process called sublimation. At 186 million miles from the Sun, the surface of 3I Atlas should be extremely cold, limiting how much ice can turn directly to gas. The Sun delivers specific amounts of energy based on distance. At Earth's orbit, solar energy provides about 1,300 watts per square meter. For perspective, the Sun delivers more energy to Earth in 1 hour than all of humanity uses in an entire year. At 180 million miles, where 3I Atlas currently travels, that energy drops to roughly 300 watts per square meter. This represents the total solar energy hitting the surface, but not all of it goes into heating ice. Much reflects off the surface, much radiates back out as infrared heat. Only a fraction actually drives ice sublimation from solid directly to gas. Carbon dioxide ice forms the main volatile component on 3I Atlas. CO2 ice sublimates at minus 78 degrees Celsius. At the solar energy levels present at 186 million miles, scientists can calculate exactly how much ice should sublimate per square meter per second. Avi Low performed this calculation. To produce the mass loss rate observed in the November images, you would need about 620 square miles of active surface area, all sublimating at maximum efficiency. Every square inch would need to be actively converting ice to gas at the theoretical maximum rate. But the actual surface area tells a different story. NASA released an image from the Mars Reconnaissance Orbiter captured in early October. The image shows 3I Atlas as a soft, glowing white ball. The cloud of dust and gas around it measures approximately 932 miles in diameter. The solid nucleus doing the actual sublimating is much smaller. Based on earlier measurements, the nucleus spans only a few miles wide. This gives it maybe 30 to 40 square miles of total surface area. Even if we assume maximum exposure and activity across the entire surface, this falls far short of the 620 square miles needed to explain the observed mass loss. The math simply does not work. You cannot generate this much material from heat-driven ice sublimation with the available surface area. The physics equations that govern every other comet fail to explain what 3I Atlas is doing. Sometimes comets resolve this problem by breaking into fragments. When comets reach their closest approach to the Sun, tidal forces and thermal stress can shatter them. More fragments mean more total surface area for sublimation. Multiple pieces can produce more gas than a single nucleus. But images from November 11th showed one single intact nucleus. No fragments appeared. No debris. Cloud surrounded the main body. Just one solid object maintaining its structure while somehow producing mass, loss rates that require 20 times its available surface area. The brightness anomaly adds another layer to the mystery. Comets follow predictable brightness curves based on their distance from the Sun. As they approach the Sun, increasing heat drives more sublimation, creating a thicker coma that reflects more sunlight. After passing perihelion, their closest point to the Sun, they move away and cool down. The brightness drops off predictably based on distance. 3I Atlas passed perihelion over a month ago. At 180 million miles distance, the solar heating has dropped significantly from peak levels. Activity should be declining. The coma should be thinning. The brightness should be fading according to well-established formulas. But the November images show strong, sustained brightness. The coma still glows intensely. The tail structures remain prominent and well-defined. There is no sign of the expected dimming that characterizes comets moving away from the Sun. To maintain this brightness level, Avi Low calculated the object must be losing about 200 tons of material per second. This enormous ongoing mass loss rate should not be possible for an object that is cooling down and moving into colder regions of space. Consider what 200 tons per second means over time. If 3I Atlas has maintained this loss rate since perihelion, the total adds up to billions of tons of material shed. For an object estimated at 33 billion tons total mass, this represents roughly 10% of its entire mass lost in just 2 months. A natural comet experiencing this rapid mass depletion should show dramatic changes. The nucleus should shrink visibly as layers peel away. The activity should sputter and fluctuate as internal structures fail and collapse. The ice pockets should deplete unevenly, creating chaotic outbursting patterns. None of these expected changes are happening. 3I Atlas maintains its single intact nucleus. The jets remain stable and focused. The brightness stays anomalously high. The 5-to-1 tail ratio persists unchanged. The geometry of the tail structures reveals more problems with standard models. The anti-tail pointing toward the sun should not exist at this distance with this intensity. Solar radiation pressure increases as the square of distance. At 186 million miles, the pressure pushing particles away from the sun has dropped to less than a quarter of what 3I Atlas experienced at Earth's distance. Yet the anti-tail extends 600,000 miles directly into this solar wind. The particles must have tremendous initial velocity to overcome the constant opposing force. They must also have sufficient mass to resist being turned around by radiation pressure. The physics requires either extremely high ejection velocities, far beyond what sublimating ice produces, or particle masses much larger than typical comet dust. Both scenarios contradict standard comet behavior models. The toward-sun tail also maintains remarkable consistency. Across 600,000 miles, the structure stays columnated without dispersing. Normal dust particles would spread laterally due to different orbital velocities. Particles ejected at slightly different angles would diverge over these distances. To maintain such focus requires either active confinement, like a magnetic field channeling charged particles, or an ejection mechanism that produces nearly identical particle velocities. Neither explanation fits the standard comet model. The away-from-sun tail extends 5 times longer at 3 million miles. This tail has solar wind assistance pushing particles outward, yet it also maintains unusual focus. The narrow beam structure persists across distances where particle dispersion should create a wide fan. The temperature at 3I Atlas's current position should be approximately minus 130 degrees Celsius based on solar heating alone. This is cold enough that water ice remains completely frozen. Only supervolatile ices like carbon dioxide and carbon monoxide can sublimate at these temperatures. But even CO2 ice sublimation cannot explain the observed activity. The available solar energy, the limited surface area, and the distance from the sun create a physics problem with no solution in standard models. The stable 5-to-1 ratio between tail lengths suggests a consistent underlying mechanism. Random outgassing from different ice deposits would create varying tail proportions as the object rotates. Active regions would strengthen and weaken. The ratio would fluctuate. Instead, observation after observation shows the same proportion. The November 22nd image matches the November 24 image. Earlier observations align with current ones. Whatever drives these jets operates with mechanical consistency. The Mars Reconnaissance Orbiter image provides crucial scale. The 932-mile diameter coma seems enormous, but it consists of extremely diffuse gas and dust. The actual solid nucleus generating all this material occupies a tiny fraction of that space. Think about the size mismatch. A nucleus just a few miles wide creates a glowing cloud nearly 1,000 miles across. It maintains 2 jets extending millions of miles. It loses 200 tons of material per second. The energy budget does not balance. Standard heat-driven sublimation at this distance should produce minimal activity. Other comets at similar distances show faint, diffuse comas and weak tails. They follow predictable brightness curves that dim rapidly as they recede from the sun. 3I Atlas breaks these patterns. Its brightness remains anomalously high. Its jets stay focused and stable. Its mass loss rate defies the available energy input. Every measurement reveals behavior outside normal comet physics. The single intact nucleus eliminates fragmentation as an explanation. When comets fragment, the pieces typically separate and follow slightly different orbits. Each fragment develops its own coma. The overall brightness might increase temporarily, but the mass loss spreads across multiple sources. The November 11th images show none of this. One solid body generates all the observed activity. No companion fragments trail behind. No debris field surrounds the nucleus. Just one object somehow producing effects that should require 20 times its surface area. The toward Sun anti-tail represents the most puzzling feature. Creating this structure requires ejecting material with enough velocity and mass to push directly into the solar wind for 600,000 miles. The particles must maintain cohesion while fighting constant opposition. Typical comet dust particles have sizes measured in micrometers. Solar radiation pressure easily deflects such small grains. To create an anti-tail, the particles need sufficient mass to maintain momentum against this pressure. The density calculation by Low quantifies this requirement. 1 million times the solar wind density means these are not normal comet dust grains. The mass concentration in the anti-tail exceeds anything produced by standard sublimation processes. The columnated nature of both tails suggests directed ejection rather than random outgassing. When ice sublimates from a comet surface, the gas expands in all directions. Dust particles get carried along chaotically. The result should be diffuse, expanding clouds, not focused beams. Laboratory experiments with sublimating ice under vacuum conditions show rapid dispersion. The gas molecules fly apart immediately. Any entrained dust spreads into a wide cone. Creating a narrow jet requires special conditions not present in simple sublimation. The stability over time makes the mystery deeper. 3I Atlas has maintained these features across millions of miles of travel through space. The solar heating has changed. The angle relative to the Sun has shifted. Yet the jets persist with consistent geometry. Most comets show dramatic activity variations. As they rotate, different regions face the Sun. Ice pockets exhaust. New areas become active. The result is constantly changing jet patterns, fluctuating brightness, and evolving tail structures. 3I Atlas shows none of this variability. The November observations match earlier ones. The 5-to-1 ratio holds constant. The jets maintain their focused appearance. Something keeps this system locked in a stable configuration. The mass loss rate creates a survival problem. At 200 tons per second, 3I Atlas should be visibly shrinking. 10% mass loss in 2 months projects to complete destruction within a year at this rate. Yet the nucleus remains intact with no signs of imminent breakup. Natural comets cannot sustain such loss rates without showing structural failure. The ice binding the nucleus together would deplete. Rocky components would separate. The object would fragment into a cloud of debris. The brightness should also vary as the viewing angle changes. We see 3I Atlas from different perspectives as both Earth and the comet move through space. Different illumination angles should create brightness variations. Active regions rotating in and out of view should cause fluctuations. Instead, the brightness remains anomalously stable and high. The intense glow persists regardless of viewing geometry. The coma maintains its luminosity even as the object recedes into colder space. The energy paradox cannot be resolved with standard physics. At 300 watts per square meter of solar input, with typical albedo and thermal properties, the available energy falls far short of requirements. You need either a much larger surface area or a different energy source. The intact nucleus rules out larger surface area from fragmentation. The stable structure eliminates chaotic sublimation from internal collapse. The consistent jet geometry contradicts random outgassing patterns. Every observation adds constraints that standard models cannot satisfy simultaneously. The mass loss rate requires more surface area than exists. The brightness needs more energy than arrives from the sun. The anti-tail demands particle properties beyond normal comet dust. The detection of these features by multiple independent observers removes any doubt about their reality. The November 22nd observation used a half-meter telescope optimized for faint objects. The November 24th observation confirmed the same structures despite challenging viewing conditions near the horizon. Amateur astronomers around the world are documenting identical features: the narrow jets, the 5-to-1 ratio, the sustained brightness all appear consistently. This is not one anomalous observation, but a pattern confirmed across multiple instruments and locations. The distance from the Sun makes these observations even more remarkable. At 186 million miles, 3I Atlas should be fading into obscurity. Most comets become invisible to amateur telescopes long before reaching this distance. The fact that clear structure remains visible indicates exceptional ongoing activity. 3I Atlas continues to break the fundamental rules governing comet behavior. The physics that explains every other comet in our solar system fails to account for what we observe. The measurements are clear, consistent, and incompatible with standard models. The anti-tail extending toward the Sun should not exist with this intensity at this distance. The mass loss rate exceeds what the available surface area can produce. The brightness remains too high for an object moving away from the Sun. The jets stay too focused across millions of miles. These are not minor discrepancies, but fundamental violations of established physics. The energy budget does not balance. The mass loss cannot be sustained. The geometry defies standard ejection mechanisms. Yet observation after observation confirms these impossible features persist.